Hello, calculus class. Sorry that I cannot be with you today, but I'm leaving you this video, and hopefully you will have the opportunity to work on your homework before class ends. Okay, that is my goal. So, I'm still going to act like I'm there, and I'm still going to ask you questions and expect you to talk to each other. So the first thing I'd like you to discuss with the people at your pod is how could the second derivative help us with relative extrema? Brainstorm, talk amongst your pod, see what you can come up with. Okay, hopefully you've had a little bit of conversation. What I would like to point out are the relative minimums and maximums here on this graph. Now, first of all, what do we know about the first derivative there? We know that at our relative extrema, our first derivative is either going to be 0 or undefined. Okay. Now, what I want you to notice about these minimums and maximums, okay, since we're talking about the second derivative, let's focus on concavity. Okay. Turn to each other. What is true about the concavity at the relative maximums? Okay.
Kylie Sacker, please come to the shield. Kylie Sacker, please come to the shield.
Now turn to each other and comment about the concavity at the relative minimums. Okay. Notice that our concavity at our maximums is concave down. The concavity at our relative minimums is concave up. That is a pattern. Okay, so on Wednesday we discussed the first derivative test to help us find minimums and maximums, relative minimums and maximums, excuse me. The second derivative test does the same thing. It helps us identify relative minimums and maximums. However, it uses the second derivative instead of the first derivative. Okay, so first of all, we have a function that has a critical value, and the derivative at that critical value is 0. Okay. If our second derivative exists, then if the second derivative at that critical point is positive, meaning we are concave up, then we have a relative minimum. Okay. Think about the picture that was on the previous slide. If our second derivative at that critical point is negative, then we know we are concave down, which means that critical point is a relative maximum. There's your visual. Okay, now the unfortunate thing about the second derivative test is that if the second derivative is 0, then we cannot determine if it is a relative minimum or maximum. Okay, we say that the second derivative test fails. It could be a minimum, it could be a maximum, it could be neither. Okay, so if you are using the second derivative test and your second derivative is 0, then you have to go back to your first derivative and use the first derivative test. Okay? So here are the steps that I would like you to take in order to use the second derivative test to find relative extrema. First of all, you're going to need to know your critical values. That's going to be true no matter what test you are using. Okay? Your critical values are where we have potential minimums and maximums. You need to then find the second derivative, since we are using the second derivative test. And then you need to evaluate the second derivative at your critical values. That will tell you your concavity, and then we can decide whether our critical value is a minimum or a maximum. So we're going to do 2 examples, and then the rest of the time will be yours to work on your assignment. Okay? So go ahead and copy down this first example. Your first step is to find the derivative. So your derivative should be negative 4x cubed plus 12x squared plus 16x. We then need our critical values, which means we need to set this equal to 0. Okay? I see that we have a GCF of negative 4, so let's go ahead, negative 4x. Let's go ahead and factor that out. Left over is x squared minus 3x minus 4. And then x squared minus 3x minus 4 can be factored to x minus 4 times x plus 1. So our critical values are x is 0, x is 4, and x is negative 1. Okay? Now, our first derivative test, yes, we would put these on a number line. Okay? But we are talking about the second derivative test, so we need the second derivative. So let's go back up here. Here's our first derivative. Our second derivative means we're taking the derivative of the derivative. That would be negative 12x squared plus 24x plus 16. From here, all we need to do is determine whether our function is concave up or concave down at these particular critical values. So let's go ahead and discuss the second derivative evaluated at 0. The second derivative evaluated at 0 is 16, which is a positive number. If our second derivative is positive, that means we are concave up, which means our critical point is a relative minimum. So we have a relative minimum at x equals 0. by plugging in x is 0 into our original function, that minimum is at the coordinate 0, 0. Let's move on to our second critical value, 4. If we plug 4 into our second derivative, we get a value of negative 80. Negative 12 times 16 plus 24 times 4 plus 16 is negative 80. That is a number that is less than 0, which means our function is concave down there. Remember, concave down looks like this. And if we have a critical point where our derivative is 0, okay, that means this coordinate is a relative maximum. If we plug 4 back into the original function, we get a y value of 640. So we have a relative maximum at 4, 640. I understand that you're probably going to need to use a calculator to get 640. It would not hurt to check me as I'm doing this, okay? I understand that you would need to use a calculator to get 640. That is fine. Know that on the non-calculator portion of your quiz or test, I would make sure that the values were reasonable in order to plug in and multiply, add, that kind of thing. All right, and last we need the second derivative at negative 1. If we plug in negative 1 to our second derivative here, negative 12 times 1 plus 24 times negative 1 plus 16, that gets us a negative 16. Negative 16 is less than 0. If our second derivative is negative, that means we are concave down, which means our critical point is a relative maximum. By plugging negative 1 back into the original function, we get a y value of 3. So negative 1, 3 is also a relative maximum. And that is the second derivative test. Okay, so moving on. Please write down this example. So our first step is to find the first derivative, another nice polynomial. Our first derivative is negative 15x to the 4th plus 15x squared. We need critical points, so we're going to set this equal to 0. I see that we have a GCF of, I'm going to say negative 15x squared. So left over is x squared minus 1. So our critical values are x is 0, positive 1, and negative 1. All right, so now our second derivative. Our second derivative, and I'm going to come back up to here, Please don't come to here and use the product rule. Go back to just your original first derivative. Our first derivative, if we take the derivative of that, negative 60x cubed plus 30x. So second derivative test, we need to take our critical values and plug them into the second derivative. The concavity will tell us if they are a maximum or a minimum. If we plug 0 into our second derivative, what happens? Why did I put a frowny face? If our second derivative is 0, that means the second derivative test fails, and we have to fall back on the first derivative test. Okay? So, really, since my first value failed, we could plug in 1 and negative 1 into the second derivative, but we're going to have to fall back on the first derivative test, so we may as well just make our number line now. Okay, so I'm going to make a number line. Remember, for the first derivative test, we have to make a first derivative number line. Remember, we're plugging these intervals into the first derivative. Okay, so back up to here. If we plug a number to the left of negative 1 up there, looks like we're going to get a negative first derivative. If we plug a number between negative 1 and 0 into that first derivative, looks like we'll get positive. Hope you're doing this along with me. If we plug a number between 0 and 1 into that first derivative, like 1/2, looks like we would get a positive value. And if we plug a number to the right of 1, we're going to get a negative value. Okay, so you can see why our second derivative test failed. We do not have a minimum or a maximum at 0 because there is not a change in our first derivative. Okay, so instead, we have a minimum at x is negative 1, and a maximum at x is 1. Okay, so if we plug those numbers in to actually get the coordinates, okay, we should get, let's see, negative 1, negative 2 should be our relative minimum, and 1, 2 should be our relative maximum. All right, so you've seen two examples, one where the second derivative test works, one where it does not, and we have to fall back on the first derivative. Okay, keep that in mind as you are going through your assignment. Good luck, and I will see you on Monday.